Great. Well, it's good to see so many people here. Must confess, I'm a little jet lagged. Because I just got back yesterday from 3 weeks in Vietnam and South Korea. So if I sound incoherent at any point during this talk or fall asleep, you know why. So this is sort of an overview of the microservice architecture. Kind of, define what it is. Explain why you would want to use it. Because certainly one thing I've noticed, it's sort of traveling around visiting clients, it's somewhat become this magic pixie dust. Oh, we just sprinkle microservices and everything will be perfect and so on. But it really isn't. There's a lot of kind of, there's a real goal to using the microservice architecture, and actually, and also in order to be successful with it, you actually have to have the right in-house capabilities as well. So I'm going to talk about the benefits of using microservices and also talking about the drawbacks as well. But before I do that, a little bit about me. I've been developing software for a long time, since the 80s, in fact. Turns out my first paid job was back in 1982, writing RPG on a mini computer, but not cool. But anyway, worked on a number of things, did Lisp. Worked on Lisp implementations for 7 years, quite a long time ago. Eventually ended up programming in Java. 12 years ago now, my book Pojo's in Action came out, and that was all about building applications with Spring and Hibernate, which were revolutionizing enterprise Java development. Then back in 2007, I started tinkering with this really obscure service known as Amazon EC2, which was from this online bookstore. Weirdest thing. Anyway, API, you could provision servers, up to 20 servers, pay 10 cents per hour per server. It was like, whoa, that's so cool. So I ended up creating the original Cloud Foundry. So that was a PaaS for deploying Java applications on EC2. Upload your WAR file, launched a bunch of instances, and configured them with Apache, Tomcat, and MySQL. And then that got acquired by SpringSource back in 2009, which was right before SpringSource was acquired by VMware. So it was all part of, well, SpringSource, VMware, and then briefly at Pivotal for like 4.5 years. And so since then, that was like 5 years ago, and since then I've been pretty much focused on the microservice architecture. Traveling the world, working with organizations, help them successfully adopt the microservice architecture through training and consulting. Also working on a startup, building a platform to simplify the development of transactional business applications that use microservices. And I'm in the middle of finishing a book, which actually should go to press this week. It was funny, with my trip to Vietnam, I was working with a client all day, and then in the evenings I was reviewing proofs. So didn't actually do any sightseeing. Anyway, book should be out. Well, the early access version's been available for quite a while now, but the actual printed version should be available real soon. And you can get a discount, 40% off today only with that discount code. Now I also work on microservices.io, so that's sort of a destination site where you can learn all about the microservice architecture. And a bunch of what I'm talking about today really comes from that site. And we're actually going to be introducing some tooling, like self-assessment, so you can evaluate your microservice architecture and identify the weaknesses, and it will provide guidance on how to improve them. Anyway, enough about me. Let's talk about microservices. So kind of compare. It's going to begin by comparing the monolithic architecture with the microservice architecture and explain why you would want to use it. Then I'm going to talk about some of the challenges with using microservices, how they're not actually a silver bullet that if you simply start using them will make everything perfect. And then I'm going to finish up talking about the microservice pattern language that's a collection of architecture, design, development, and operational patterns that can help you successfully apply the microservice architecture. So that's me. And remarkably, I've been talking and I still have 50 minutes remaining, so I'm not quite sure how that works. Okay, so let's imagine that you were going to build some, cool new application, right? I'm a foodie, and so like everything I do somehow involves food. So my example application in my book is a food delivery application. I think now it would be cool, like online, real-time logistics application, which sounds fancier. But imagine you were building an application like that. You would most likely come up with an architecture that looked like this, right? So internally, it would be layered. It would have modules corresponding to different sort of functional areas of the business. Order management, delivery management, restaurant management, and so on. So it actually would have structure to some extent. But then from an actual packaging and deployment perspective, what you will then do is just package it up as a single application. In the Java world, that would be a WAR file or an executable jar. I guess some other language, there's just this notion of an application. And I think, if you're a startup, it's really common to just build the application. So your entire business is just a single application, single code base, which is kind of interesting, because at some level, this is not a bad idea, right? The monolithic architecture, just building something as a single application, is not actually an anti-pattern. There are many situations in which this is the appropriate architecture for your application. It actually gives you can successfully develop software this way. But the problem you have is if you're successful, your application has a habit of growing. Like you go read some classic book on software engineering, there's this notion, you do requirements, then you build it, and then there's this maintenance phase, right, where you somehow maintain the application. But in reality, applications, we never stop developing. They just keep growing. Those marketing people come up with new features, and we keep having to add them, right? So the application just keeps growing. And then because we're making money, or at least we're getting lots of VC funding, because companies don't seem to make money these days, we can hire more people. And the team keeps growing, right? And then eventually we might divide up into these sort of different teams focused on particular functional areas of the product. So we've got lots of people organized into teams. We've got this massive code base. And eventually, you're going to end up with a huge application. I've talked with clients where, they say they're a 10-year-old company and they have 100 developers, and their application is measured in gigabytes. I'm trying to remember what the largest one was. Maybe it was 5 or 10 gigabyte application. And these are actually successful companies, right? I mean, it's like the unsuccessful ones, they go out of business and they don't have any problems with large code bases. But, unless you're lucky, eventually you're going to end up in this place where development becomes quite slow and quite painful. The code base is beyond beyond the comprehension of an individual developer. The sheer size of the application makes testing a slow, painful process. And likewise, deployment is this slow, painful process. You end up in what I call monolithic hell. Just because your application has really outgrown its architecture. And then not only that, another sort of side effect of this is that you tend to be locked into the particular technology stack that you picked at the start of development. Your code, it just simply is too expensive and too risky to migrate your entire application to a large code base. So and then there are other sort of side effects, like modularity tends to break down, and and your architecture sort of slowly degrades into a big ball of mud. So So it's kind of deeply problematic. And I'm not saying it's inevitable, but it does seem quite likely that given enough time, you will end up in this situation. So, this is a problem. I mean, I kind of hate the phrase software is eating the world, but, there's some truth to that, right? Like, software is, become central to how businesses operate. Businesses need to innovate faster, which from a software development perspective means that we as developers need to deliver software much more quickly, much more frequently, and also in a much more reliable fashion. So the whole pace of delivery needs to accelerate. And if we've got these large, cumbersome monoliths, if that's our application, then we're not going to be able to do that. We don't have the deployability and the testability that we need to truly be competitive. And so that kind of then leads to the microservice architecture. And, the basic idea is instead of an architecture like this, we have an architecture like that where instead of one large monolithic code base or one large monolithic application, we functionally decompose our application into a set of services. And those services are loosely coupled. It means that we can easily change one without that change rippling through the system. Also, the services tend to be organized around what are known as business capabilities. So they're sort of implementing specific functional areas of the application. And that's a term from business architecture where you think, you analyze the structure of an organization, it's going to have a set of capabilities, which are basically, things that it needs to do in order to deliver value. So, online store must have an order-taking function, must have a kitchen management function that manages the preparation of the food at the restaurants. It also has to manage deliveries as well, coordinate couriers, plan their routes, and so on. So, if those are the capabilities that you need in order to operate a business, you basically map that into a technical architecture and define services corresponding to those particular capabilities. And that is an essence of the microservice architecture. It is just a kind of form of divide and conquer or modularization, where what we're modularizing into is a set of loosely coupled, independently deployable services. So what that means is if we go back and look at the food delivery application, we have a bunch of services. Because they're loosely coupled, each one of those services is going to have its own database. Services cannot communicate through databases or through database tables because that is a form of tight coupling, which actually creates all kinds of interesting challenges around transaction management and querying, which is like a whole other talk. You can also functionally decompose the web application. So that's the application running server-side that's generating HTML pages. So you can have a web application that's focused on, that's responsible for order management, another web application that's used by the restaurants or the kitchens, and so on. So different parts of your UI are implemented by different web applications. And then if you, this is like API gateway. It's kind of relevant to this conference, right? If you're exposing an API to the outside world, then you need some form of API gateway, which I should say you need to use Kong, right? Should have updated that slide. So basically, as I'm sure you all know, an API gateway sort of plays multiple sort of roles. But sort of from the pure microservice architecture perspective, it's exposing an API to the outside world. And it's responsible for routing inbound requests to the relevant backend services. So that API might be consumed by mobile devices. It also might be consumed by JavaScript running in the browser. You might in addition to HTML, maybe you have a single-page web application. That API can also be consumed by third-party developers, which actually introduces serious API management issues as well. And you might also have a gateway to handle inbound messages as well. So what's interesting about this, it already hints at one of the downsides, is like, whereas before we had one application and we just ran a few copies of that application behind a load balancer, now we've got all these different moving parts. Each one of these boxes represents a piece of software which at runtime will have multiple instances with some load balancing capability for each one. And so this is a much more complex architecture. So the services themselves look something like this. They have, from a client perspective, a service has an API. An API, and that API is comprised of two parts. There's sort of the command API, command and query part of the API, which you could implement using REST, but there are other ways to do that, gRPC, for example. It could also be done with asynchronous messaging. And that's, you send in a request, you get back a response, and the commands update data. The queries simply retrieve data. Another key part of the API is the event publisher. It's quite common for services to emit events. So for instance, when an order is created, the order service will very likely emit an order created event. When it's canceled, it's going to emit an order canceled event. Then also, the API, the service will actually have a database storing the data that it owns, and it also might store data that is replicated from other services by subscribing to the event stream. And then there's the implementation where a service rather, because it often needs to collaborate with other services, it's going to invoke commands and queries on those other services and also subscribe to their events. So this is kind of a useful kind of view of what a service is. Key part of this is that it's independently deployable. That's kind of one of the key benefits of the microservice architecture, is that we can modify a service, change its code, and redeploy it independently of all of the other services that make up our application. Enables us to develop and deliver software much faster and deploy it much more frequently. An interesting aspect to the microservice architecture is, well, how big should our services be? And one of the drawbacks of the term is that the first thing you hear is micro, right? Which makes it sound like these services should be tiny. And in fact, during the early days when people were talking about microservice architecture, people would say, oh, it should just be 100 lines of code, or you can develop it in 2 weeks. I mean, in reality, a service should be small enough to be developed and owned by a small team. The so-called Amazon 2 pizza teams, right? Which could be 6 people, 8 people, maybe as much as 15, but really, no bigger than that. The idea is that you sort of structure your organization into these small independent teams that own one or more services. So that's a good starting point. And maybe a team would own multiple services. So that's so to me, the size of a service is really not important. It should just implement meaningful business functionality and enable a team that owns it to deliver software frequently, rapidly, and reliably. So you end up with sort of an kind of organization and architecture that looks like this, where you have these loosely coupled teams that are each responsible for a particular functional area of your business. They're developing, testing, and deploying their service or their services independently from what all of the other teams are doing, at least the vast majority of the time. Obviously, if two services need to collaborate, there needs to be some agreement on what that API should be. So that's when teams would actually meet and hash out what the API to support the collaboration should be. But once they've done that, they can go their separate ways. And this is kind of one of the key benefits of the microservice architecture, is that it lets you have these small autonomous teams that are working independently the vast majority of the time. And kind of ultimately what this leads to is sort of, it basically enables you to do DevOps for style development of these large applications. So this is grabbed from the 2017 State of DevOps report. Interestingly, I went to the 2018 report recently, but couldn't find the exact same table. Well, so this is a survey of organizations about how they deliver software. And there's like 4 key metrics. So there's deployment frequency, like how often are you deploying changes into production? You know, there's also another key metric is lead time. How long does it take from when a developer commits their change, checks in some code, to that code running in production? So that's kind of measuring speed, and then the last 2 metrics are measuring reliability. You know, what's the mean time to recover from an outage? And also, then there's the change failure rate, like how often does a deployment result in an outage? So those are really the kind of key metrics that sort of assess the health of your software engineering organization. Anyway, they kind of group it into 3 categories: low performers, medium performers, and high performers. And what's interesting, right, is the high performers, they're deploying into production multiple times a day. And there's this really crazy statistic from 2014 where Amazon was deploying a change every 11.6 seconds. Obviously, massive engineering organization, right? But like, whoa. So, you know, while I've been talking, I mean, they've done hundreds of deployments. And they've done that without, you know, and they rarely have downtime, right? Also, the lead time for change, you know, in a high-performing organization is under an hour. Developer commits a change. There's an automated deployment pipeline that runs a series of automated tests. Once it's completed, that change is pushed into production. You know, and there was some story about Netflix where they were able, you know, one of their services, you could make a change to it, and it was deployed up around the world within 16 minutes. So it's all about moving fast. And then what's awesome is that they're actually not breaking things, right? So high-performing organizations are able to deliver software much more reliably, where they can recover from errors much more quickly, and their change failure rate is much lower than medium or low-performing organizations. And so this is, you know, you achieve this through a combination of the right architecture combined with, namely microservices, combined with using, you know, proper DevOps practices. And this, in a sense, is like the key benefit of the microservice architecture, right? It gives you the testability and deployability that DevOps requires, or more specifically, continuous delivery and deployment requires. And it also, the architecture enables the teams to be small and autonomous, right? This whole model of a team owns one or more services that they can develop, test, and deploy independently of what those other teams are doing. You know, that's kind of that's kind of the organizational structure that fits in with DevOps. And then, you know, this is essentially why we should be using the microservice architecture. And then there's this graph, which came out in this excellent book, Accelerate, which sort of, you know, what's really interesting is, you know, normally when you grow an organization, productivity drops because you spend all your more and more time in meetings. Kind of the coordination costs, which are like n squared, start dominating once your organization gets quite large. But there's this great chart that shows, in these sort of kind of high-performing organizations where you've got these loosely coupled teams and a loosely coupled architecture, as you increase the number of developers, productivity actually kind of goes up, which is quite powerful, which is such an awesome concept. And then also, another great benefit of the microservice architecture is that you can experiment safely and evolve your technology stack. So for instance, you might have an all Java stack, right? And then you hear that Google uses Golang, which makes it super cool, right? So you use that. And then you realize that you really want a modern language, not like C from 1990s version of C. So you might then decide that Kotlin is better. And that's okay. You've done an experiment and you've tried using one language and decided that it wasn't a good fit for you, which is a valuable thing to know. And then later on, you can replace that service with a language that you decide is a much better fit. So that's a really important benefit of this architecture. So you can incrementally and safely evolve your technology stack over time. So a whole bunch of benefits, but there's also some significant downsides to this architecture. There really is no silver bullet in software engineering. Basically any technology has both benefits and drawbacks. That's kind of inescapable. And by far the biggest drawback of the microservice architecture is its complexity, right? From a development perspective, you're now building a distributed system. So you have to deal with inter-process communication. You have to deal with partial failure. When you invoke a service, there's no guarantee that that service is going to respond in a timely way. And also, you have to deal with distributed data. Each service is owning its data, and so sort of traditional transaction management techniques can't be used. Good news is for all of these issues, there are frameworks, but there is this kind of additional complexity that you have to deal with. Also, testing is simultaneously easier and harder. It's easier in the sense that each service is small and so easier to test, but it's sort of, you then have the issue of, well, how do we make sure that our services can actually work together? So when service A equals B, that's actually going to work. The good news is that there are testing strategies, in particular consumer-driven contract testing that you have to employ in order to do that efficiently. That actually enables you to test services independently while being confident that when you actually deploy them into production, they will actually work together. And then also from a deployment or operational perspective, it's more complex. Before, you had a monolith, one application, and you just ran multiple copies of it in production. Now, there are potentially tens or hundreds, or in some cases, thousands of services, each one of which will have multiple instances. So in production, there are just many more moving parts that you have to kind of monitor and manage. Good news is that, yet again, there are solutions to this. Modern platforms like Cloud Foundry, like Kubernetes, and all of sort of all of that deployment technology goes a long way to tackling this complexity. So yeah, it's like more complex, but on the other hand, your monolith is complex, and there isn't much you can do about it, and it's just going to get more and more complex over time. You also have to figure out, are microservices a good fit for my application? Is it complex enough to justify using the microservice architecture? If you're a team of 2 people, probably not. If you're a team of 30 people, quite possibly. The actual answer is a little bit more complicated than that. It kind of depends, because I've worked on 2-person teams where we probably could have benefited from it. And then also, do you have the skills in place to properly use the microservice architecture? You know, a common weakness of many software engineering organizations is they're terrible at automated testing. Sure, all of you are good at it, but all the other folks that I go visit, you know, it's even though like JUnit, popular Java testing framework, is like 20 years old now, it still doesn't seem to be used widely. I mean, there was some statistic, kind of a report showing that maybe only 23% of organizations made extensive use of automated testing. Yet, if you're going to use such sort of the microservice architecture, you have to do automated testing. Not only because what you're building is much more complex, but if if your whole goal of using microservices is to deliver software frequently and reliably, well, a big part of that is automated testing, right? And also automated provisioning. You know, no more SSHing into machines and copying over files and so on. You have to have that automated. And then also when you are using microservices, there's like a whole bunch of technical issues that you have to address around inter-process communication and so on. So there's a bunch of challenges. And so that, because of that, that's kind of motivated me to create the Microservices Patterns language. So that's a collection of patterns that solve these sort of architecture, design, development, and operational problems. So if you go to microservices.io, you will see this pattern language. So just to briefly recap, right? Like, well, what's a pattern? So it has a really simple definition. It's a reusable solution to a problem that occurs in a particular context. And it was popularized by the so-called Gang of Four book, which came out in the mid-90s. And that was a collection of object-oriented design patterns, right? Singleton strategy, and proxy, and so on. But the concept of a pattern is much broader than that. There's a vast number of domains that you can use patterns in. And in fact, the original pattern concept came from real-world architecture. Christopher Alexander created a pattern language for architecting everything from cities down to like how to lay out a room, light on two sides, for example. So patterns are really useful. And one reason for that is that they really encourage objectivity. Now, today, if you think about how we talk about technology, it's usually, whoa, this is awesome, right? Oh, that sucks. Like my favorite technology rocks. Yours sucks, right? I mean, we sort of very kind of polarized positions that don't sort of properly evaluate the benefits and drawbacks of any given approach. Whereas patterns take a different approach, because if you look, so you'll see this on microservices.io. When you talk about patterns, you describe the benefits, but you also have to describe the drawbacks. Then you have to describe the issues, so which are problems that this pattern introduces. And then you also have to say, well, if you're going to use this pattern, you will have these issues, and in order to solve those issues, here are the patterns that you must apply or consider applying to address those issues. So patterns actually have relationships with other patterns. And then not only that, a pattern also should say, here are the alternative patterns, other ways of solving this same problem. So it's a much more, it's kind of a really simple idea, but it's a much more objective way of describing a technology or an approach or a solution because of the fact that it's describing the drawbacks, the issues, and then the related patterns. So this is the pattern language, which you probably can't read, but that's okay. If you go to microservices.io, there's a very readable version of that. But there's sort of different areas of patterns, top level, it's like, well, should I use the monolithic architecture or the microservice architecture? And then if you decide to use microservices, everything else on all of the other patterns apply to the microservice architecture. Then obviously the next question is, well, I'm going to use microservices. What are my services? And so there's patterns that guide you in on how to decompose into services. And then once you've done that, there's all these other patterns that you have to use to actually kind of make all of those services then work together. So it's great, we split it up, but then they have to collaborate. So there are patterns around managing distributed data and inter-process communication. And then there are operational patterns as well. How do we deploy the services? And then also, how do we do monitoring of them? So those kind of the big groups, and then there's obviously other parts of the pattern language as well. And the idea is that it just sort of guides you when you're developing an architecture. For each of the architectural and design decisions that you must make, the pattern language actually tells you what your available options are. So here are the 2 or 3 or 5 patterns that solve this problem. And then it also tells you what your trade-offs are with using them. So there's kind of the various sort of key patterns. So step number 1 is, well, am I going to use a monolithic architecture or a microservice architecture? Am I going to architect my system as a single executable or a tightly coupled set of services that, say, share a database? And sometimes that's fine, particularly if you have a small application. But then if you're building something more complex, then yes, you do need to have, structure it as multiple loosely coupled services. And then the next thing is, well, okay, if I'm going to use microservices, how do I decompose them? And there's sort of 2 main approaches. The end result are services that implement sort of the business functions, but you can either come at it from a business architecture perspective and decompose by business capability, or you can come at it from a domain-driven design perspective and sort of decompose by subdomain. The end result is actually the same. Just sort of depends on what your which school of thought you're in. Okay, so we've sort of now split up our system, but then one issue is how do we maintain data consistency? That's because in order to ensure loose coupling, each service has its own database, and the data is private to that service. So we can't actually use traditional 2-phase commit, traditional distributed transactions, because that impacts availability. And so there we end up having to use what's known as the Saga pattern, which is an eventually consistent approach. So a Saga is a sequence of local transactions that are coordinated through messaging. So quite a different way of sort of managing data consistency. It's one of the biggest challenges with this architecture. And then related to that, it's like, how do we do queries? Each service has its own database. The data is private, so we can't sort of just execute traditional distributed queries. And so there's 2 main patterns, one of which is API composition, which is where if there are 5 services that own the data that you need, you simply invoke their APIs. You just call each one and then combine the data. And that works well in some situations, but in other situations it can be prohibitively expensive. You end up having to implement what's basically a distributed query mechanism, which you really should not do. So the other pattern that you can use is called Cqrs, Command Query Responsibility Segregation, where you basically implement a database that is a easily queryable replica of data that exists in multiple services. And that replica is kept up to date by subscribing to the events that are published by the services when their data changes. So, in this replica, you can, it's constantly being updated, and then the actual structure of that replica is designed specifically to efficiently implement a set of queries. This approach is kind of analogous to dumping data from your relational database into a text search engine like Elasticsearch or Lucene or Solr to support text search queries. It just kind of generalizes it and makes it more real time by using events to keep the different replicas synchronized. And then, of course, it's like, oh, what API should we expose to the clients? And there's a lot of really interesting issues here, right? An API is often consumed by a diverse set of clients. It might be JavaScript running in a desktop browser that's got a rich, sort of display of data, or it might be a mobile application which is likely to display a lot less data. And then different clients are communicating over different networks. High-speed local area network versus, lower bandwidth, higher latency mobile network. There's usually a mismatch between what the client needs. Like the client might want to display the status of an order, but the actual information about an order might be scattered around amongst multiple services. The order service might know some aspects of it. The delivery service, probably knows where that order is at a given point in time, and sort of so on and so forth. And that kind of ties back into the API composition and so on. And then also we want to evolve our application architecture without impacting clients. So the client shouldn't actually know about individual services. And then also some services might use protocols that are not web-friendly. Internally we could use whatever protocols we see fit, whereas the web is more HTTP and WebSocket oriented. And so what that ultimately means is we need some kind of API gateway. Or should I say, we need Kong in order to kind of act as the mediator between the outside world and our internal services. So that's kind of the main pattern, this API gateway pattern. And then there's a variant of it where we have a different API gateway for different clients. So we might have an API gateway for our mobile devices, and that gateway is for the mobile applications, and that gateway is actually owned by the team that develops the mobile application. And then we might have another API gateway for the public API that's used by third-party developers, and that API gateway is owned by that team, and that's likely to be, have to deal with a whole lot of sort of API management issues, long-term backwards compatibility, which, say, the mobile team wouldn't necessarily have to deal with. So there's a couple of different architectural patterns there. A single one-size-fits-all API gateway, or an API gateway per client. So that's the API gateway. And then, obviously testing is another big part of it, right? Like, services collaborate, and how do we kind of ensure that services can actually communicate without running the expense, without having to heavily rely on, end-to-end tests, which are slow and brittle and expensive. And there's this really important technique known as consumer-driven contract testing, where we define contracts, which are basically, in a REST API, each contract would be an example HTTP request response. And so the API would be defined by a set of examples like that. And then there are tests that use those contracts to test the service, and then there are tests that use those contracts to test each of the clients. So the tests are being run at different times, but they're being driven by the same set of contracts. So fingers crossed, it does mean that the client and the service can actually work together when we deploy them into production. That actually works quite well. So those are a lot of the key kind of patterns, the key issues that you need to address that are going to sort of determine the success of your microservice architecture. And then there's a whole bunch of just generic patterns that I sort of call them undifferentiated heavy lifting. But patterns around the actual low-level details of of communication, REST versus gRPC, or which message broker to use. There's also handling cross-cutting concerns. So you should, build your services on top of a micro-chassis framework that deals with all of the kind of basic concerns like logging, externalized configuration. Deployment is another issue. I mean, what's interesting is that's kind of the primary focus in many ways. When people talk about microservices, it's Docker, 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 right? Yet, in reality, there are many different ways of deploying your services, and each with differing trade-offs. And it's kind of a detail to some extent. And then there's sort of mechanisms around service discovery. This is becoming less of an issue because platforms like Kubernetes take care of this for you, but you can implement it at the application level as well. And then you also have to have in place the right monitoring, right? You've got to have the basics like log aggregation. You should implement distributed tracing so you can visualize the requests flowing through your system. You should capture and aggregate metrics and alert on them, and so on and so forth. Those are all important issues. They're important. You have to do them right, but it's sort of not really, that's not where you're going to compete. Having the right set of services is kind of way more important than that. Anyway, so that's pretty much my talk. Hope you found it interesting. So just to summarize, right, the goal of architecture is to satisfy sort of non-functional or quality attributes like deployability and testability, right? And those, given that software is eating the world and we need to deliver software much more rapidly, much more reliably, and so on, you want to pick the architecture that best enables that. And if you have a small application, the monolithic architecture could very well be just okay. But if you've got a large, complex application with a large team, it's quite likely that the microservice architecture will be a better fit. And you should use the microservices pattern language to, there to guide your decision making. So it's pretty much all I have to say, except to, remember my book is 40% off today, just today only. And yeah, if you want to know more, you can kind of go to that link, and there's my contact info. So thank you for listening. Hope that you found it useful.
Big round of applause for Chris. I think we're going to open up for a little Q&A. We've got about 5 or 6 minutes.
Oh, sure, yeah.
Jet lag okay with that?
Yeah. It's actually talking is okay. It's when I stop talking that I'll just pass out.
We'll keep that going.
Yeah.
Any questions for Chris? Yes. Sorry, we're going to bring over a box for you.
Whoa, what's with the box?
It's recording everything.
It's actually a basic question, but that's okay. When you have these small snippets of databases, what is the best practice to sort of consolidate data across the microservices architecture?
Yeah. So I think maybe what you're getting at is like for reporting purposes, say, or analytics. So kind of the model is, so each service is owning its own data. That data is private to that service. And then when the service changes that data, like an order is created or canceled, that service will emit an event. Order created event, order canceled event. And then interested parties can subscribe to those events. And so let's say that you want to do some kind of reporting on the entire state of your system, right? So you could write a service that subscribes to all of the relevant events and uses those events to maintain a replica, the appropriate replica of that data. Effectively, it's event-driven ETL, and then you could run reports on that data, against that replica.
So, the question. Thank you for the answer. If in future where we're getting data streams live, and then sort of doing AI and ML sort of pattern recognition on top, in real time, how do you see the aggregation of data, and what microservices play a role in that? Oh,
yeah. I mean, it's possible. I mean, it sort of depends on your specific use case and what you're really getting at there. I mean, it's possible that this architecture is entirely orthogonal to the kind of problem that you're trying to solve. I mean, though, having said that, I mean, if you've got sort of some, streaming architecture, right? You have a stream of events, I mean, which is essentially a form of pipes and filter architecture. The individual nodes in that that are processing the data or transforming the stream of events that are coming in. I mean, that's very amenable to the microservice architecture.
Chris, what are 2 or 3 problems that you see consistently across the board among projects?
Oh, yeah. So, I mean, a number of things come to mind. I mean, one problem I've seen is, that kind of like, say, a CIO gets excited about microservices and then just announces that everyone should be doing microservices. I mean, it happened with at least one client I had where they read an ebook that I wrote and got super excited. I mean, on the one hand, it's like awesome that leadership is promoting the improvement of software architecture. But in reality, what's actually better is to say, if you think about those metrics around deployment frequency and lead time, that should be your goal, say. And then the individual teams should have the ability to decide the architecture that is best in order to achieve those metrics. So in a sense, the goal should never be the microservice architecture. The goal should be deploying multiple times a day with minimal lead time. So that's one. I mean, as I mentioned earlier, I mean, a huge thing is the state of automated testing within organizations does not seem to be that good. Can anyone here actually go, yeah, we're doing it really well? Anyone? Awesome. Yeah. Which is, yeah, I mean, as I said, I think there was some statistic, and it was like 23% of organizations were relying heavily on automated testing, but it was like only 6% of organizations actually, exclusively did automated testing. So that means the other 75% are doing a large amount of manual testing. And so it's sort of like, yeah, we want to use microservices so that we can deliver software quickly, but at the same time, you don't actually have this kind of the capabilities in place to do that. And it's sort of like, I mean, I make the joke about so in a sense, microservices is like getting a Ferrari, but then if you've got manual testing, it's like pulling your Ferrari around by a horse, right? Makes no sense. Actually, maybe a more realistic one. I don't even know if this is true, but it was like, in the early days of automobiles, someone had to walk in front with a red flag to warn people that a car was coming, right? And that may be more, that's sort of kind of represents a more general problem where, you know, like if you're not doing automated testing and then your corporate policies are, well, you can only deploy once a month into production at midnight on a Saturday, right? That is in complete or defeats the purpose of using microservices. So there's a sort of I mean, I see those issues a lot.
Other questions? Yes, sir.
In reality, I mean, practical, how much you are handling this versioning? Like, because in general, they say we don't create multiple versions.
I just find it weird that people are talking into a blue box, but it really, yeah.
Yeah, so they say avoid versioning your services because at some point of time it's going to be unmanageable. So in practically, you know, in reality, how much percentage, you know, is being added in terms of services and versioning, or how do you handle that?
Yeah. Well, I mean, services do evolve, right? And I mean, there's sort of two levels of evolution. One is, well, you're changing the implementation. I mean, which in theory, well, that's just happening all of the time, right? So there's kind of the internal stuff. And there, the primary issue is, well, when you're rolling out a new version, you want to make sure that you haven't broken anything, right? So then that gets into kind of modern deployment practices like, you know, canary deployments and the like. And then the other issue you have is sort of at the API level when, well, we're going to roll out we're actually making changes to the API of our service. So number one, you should make sure that you should strive to make backwards compatible changes, which are basically additive, right? So like adding optional parameters to the request and then adding additional attributes to the response, but writing clients in a way that so they can ignore them. And then when you make a backwards incompatible change, a service will likely have to support the old version and the new version of the API for some time until you've persuaded everyone in your organization to upgrade. So it's a bunch of work, right? Whereas in the monolith, you just change everything in theory and build it, deploy it, right? So yeah, so changing your internal APIs in this world is more complex. But one would hope, which is part of the challenge, that you decompose in a way that you're not constantly changing your APIs in an incompatible fashion and which causes the changes to ripple throughout your architecture.